Welcome to our discussion of thermal expansion. Now, when the temperature of a substance is increased, we know that the materials tend to expand, most of them. And we're talking about not just solids, but even liquids and even gases. And when the temperature decreases, they contract. On a microscopic level, that thermal expansion is due to that average change in the separation between the molecules. You see, hopefully you recall that I said earlier, the average kinetic energy of the molecules, or the atoms, are directly proportional to the temperature in Kelvin. So as you increase the temperature in Kelvin, you increase the average kinetic energy of the molecules. So imagine thinking of a crystal lattice, and you can just sort of envision that these are atoms here, and that what's keeping them together are really forces, but we'll just imagine that they're like little springs, and that these atoms can basically oscillate back and forth. And so really, in a solid form, no matter what temperature it is, except for 0 Kelvin, they are always vibrating. But as you increase the temperature, the kinetic energy of those molecules start to increase, and they start to vibrate with larger amplitudes, and then hence the atoms start to separate further from one another. So that's what's happening microscopically, and you should understand that. Let's talk about it in terms of what are the variables that affect the amount of expansion. Now, when we look at the expansion just along one direction, that's called linear expansion. So if we take this bar, for example, it has original length L0, all right, and then you heat it up to a new temperature, T, then you'll see that the bar has expanded a distance of delta L. That change in length depends on three important factors. The length of the bar initially. So if the bar was like 1 meter, and it expands, say, I don't know, 0.1 meters, but if you decided to make a bar that was 2 meters now, then now your expansion is going to be twice as much of what it was before, and so now it'll be 0.2 meters in expansion. So the change in length is directly proportional to the original length. The change in length, we know, as we said over here, depends directly on the change in temperature. And the last piece that you can see in here is that change in length is depending on the coefficient of expansion. Now that's proportional, and this means that is the coefficient of linear expansion. That is just a property of really the different types of materials that you use. See, wood and crystal lattice, for example, vibrate in different ways, and so they all have different coefficients of linear expansion. So you can write the final length of this object as really the initial length plus the change in length, and then if you were to add that expression into here, you can get this one. But this is the way it appears on the AP formula sheet. Just a couple quick notes about where you have hopefully seen some of this idea of thermal expansion. Really, before even the physics came about, people have been accounting this for many years. If you think of, for example, in the construction business, and you start to put down railway tracks, for example, and if you don't put expansion, put little space between each track and the next track, you're going to have a problem where if it heats up on a really hot day, the tracks can buckle and start to bend. Let me show you a picture of that. Here's a picture of a railway in the United States that was buckled under a really hot temperature. And over here on the right is a picture of an expansion joints that you see commonly on bridges. If you've ever looked at the sidewalks closely, ones made out of concrete, they normally will put spacing between the paving blocks, because if you don't, cracks would appear due to the expansion and the contraction brought about by the difference between the summer and the winter temperatures. It's probably more common to see these type of things in a climate where you have extreme changes in temperature, such as up in Canada, where you have a really hot summer sometimes and then very cold winters, and so you have to compensate for this change in temperature. Okay, I believe you're ready now to tackle on example number 2.